So today we're going to talk about balancing chemical equations. Keep in mind what's the purpose of getting balanced chemical equations. We started with description of chemical changes, and that is language dependent. If you go to another country at a different language, people cannot communicate with each other regarding the chemical changes. So then our ultimate goal is to arrive at a system that doesn't matter where you go in the world, and if people got properly trained in chemistry, they can actually write down the symbols, the chemical equations, and everybody will understand the particular chemistry, the chemical reaction it represents. The principle, as it is, as we always say, in a chemical change, you have to obey the law of conservation of mass. Is as simply as it states, mass is neither created nor destroyed during any chemical reactions. How many grams of reactants you started with the chemical reaction, you're going to get exactly the same number of grams as products. The other interesting observation coupled with the law of conservation of mass is for all the chemical changes, no atom is altered on the level of a nucleus, which means the number of protons stays the same, and it does not change the identity of the elements, all the elements involved in the chemical reaction. It's no new atom is created, nor any existing atom will be destroyed. So if you couple these two together, you arrive at a fairly interesting conclusion. For all the elements that are involved in this particular chemical reactions, chemical changes, the total number for each element cannot change. In other words, the total number of atom for a given element during a chemical change is conserved. So the one on the reactant side has to match exactly the total number of that particular element on the right side, which is the product side. So actually we have that's formed the foundation we are going to based on the application, what we call the balanced chemical equation. The balanced chemical equation is the true universally understandable representation of chemical reactions. The goal is to properly balance chemical equations that have perfect match of total number of atoms for each element. That means perfect match means for any given element, the number has to match. Any given element, this number has to match. The second one, it's a subtle but significant one. We're going to come back and talk about it. Is you should have a simplest set of integers and coefficients. Well, we talk about why the coefficients has to be integers, because we have the coefficients define how many of each molecules or element involved in the chemical reactions. You are impossible to get a fraction of the whole molecule. So this is only the one describing how many molecules are involved in a particular chemical reaction has to be integer. So for any given chemical reaction, elements and compounds involved are set. Like if you have hydrogen gas plus oxygen gas, and it forms water vapor. So the formula for hydrogen gas, H2. Formula for oxygen gas, O2. Formula for water is H2O. It's set in stone. You're not going to change it. So you cannot change the subscript of any given compound or element. Otherwise, you're going to change the identity of the compound or the element. So only thing that can be changed is how many you have for each particular compound or element. In this case, only the coefficients. Only the coefficients can be changed. Only the coefficients can be changed. But the subscripts for anyone, let me repeat, cannot be touched. Only coefficients are allowed to be changed. So now, as I always stated, a lot of the things, a lot of the stuff that's happening in chemistry, we're talking about processes, and this particular process, I'm going to lay it out to you in step fashion. You take the description of the chemical reactions, chemical changes, and then you write skeleton equation. Key part for that, you got to identify, be able to pick up the proper information. What are the reactants? What are the products? Using the arrow to separate the reactants, and the product using the plus sign to separate the reactants, and to separate the products. Right now, I cannot emphasize enough, it is critically important. You have to be able to look at the name of the compound or the element and to translate them properly into the formulas or formula units for the ionic compounds. We did a lot of this exercise. If you cannot do this step correctly, you are in deep trouble, because then there's no way any subsequent action will get you the correct answer. So after you did that, you make an atom inventory on each side. I will show you detail in the subsequent slides how you do that. Essentially count how many of any given elements for each side, either on the product side or on the reactant side. You select the elements as different number of atoms from one side to the other and find the least common factors for the two numbers. And adjust proper coefficients to get the total number of atoms matched for both sides. And it's seemingly a simple statement here, but in practice, it's actually quite complicated, because if you change any coefficients on the compound, you change the number of a number of atoms associated with a specific element for the whole compound. It will become clear when we go to the examples. So each time a coefficient is adjusted, redo the atom inventory on the side of a chemical equation. This is critically important. You have to recount them, record them, so that's why you're not going to be confused in subsequent steps. And repeat the process until the total number of atoms for each element perfectly matches on both sides of the chemical equation. This is where you arrived at the ultimate goal of balanced chemical equation to properly represent the particular chemical changes or chemical reaction. Okay, let's take a look at examples. Example 1, we have this. I just said it previously. It's a hydrogen gas, H2G and O2G, and you can make a water vapor. And how you do the atom inventory, I generally do a vertical line, visually separate the reactant side from the product side. Then I write it down what types of elements that are involved. In this case, 2 types, hydrogen and oxygen. And start counting. I have 2 hydrogen on the reactant side and the 2 oxygen on the reactant side. Then I switch gear to count on the product side. I have 2 hydrogen atoms and 1 oxygen atoms. The hydrogens are balanced because you have 2 on the reactant side and 2 on the product side, but the oxygen atom is not. You have 2 on the reactant side, only 1 on the product side. So this is unbalanced. We have to go to the balanced chemical equation. How to do that? And you just simply choose that one. And remember now, only the coefficients can be changed. So you can have, only thing you can have the oxygen go to 2 is to put a 2 in front of the whole water molecule. And then immediately start recounting. And now you start seeing, if I put a 2 in front of the water molecule, H2O. I change the number of counts on hydrogen 2, so it becomes 4 and 2. Now looking at it, oxygen is fine, but hydrogen is not. So then you're going to move back to the reactant side, and how you're going to address this. And this will be putting another 2 as a coefficient in front of hydrogen. Now you have 4 and 2, 4 and 2, 4 hydrogens, 2 oxygens. If we use the smiley face as matched, so we should say alternatively call it balanced. For hydrogen you are balanced, for 4, and for oxygen you are balanced. And now you are achieving the ultimate goal of balanced chemical equation. So this is at two hydrogen molecules react with one. By convention, one we do not actually write it with one oxygen molecule to form two water molecules. The two water molecules. This is a balanced chemical equation that truly represents the particular chemical reaction. All right, here's the exercise and the balance of the following chemical equations. Nitrogen gas plus oxygen gas give you dinitrogen monoxide. Pay attention to the names. And also subsequently H2O2 is actually a different compound. H2O2 is called hydrogen peroxide. It decomposes, gives you water, H2O, and oxygen gas. The third one will be nitrogen gas plus hydrogen gas and form ammonia gas. And please pause the presentation and try to get a piece of paper and try to follow through on the process I just laid out in the previous slides. I pause for 10 seconds, give you time to catch up, and I will show you the proper answer so you can check your work. Okay, here comes the answer for the exercises. You need to have two nitrogen molecules and one oxygen molecules. Then you can form a two dinitrogen monoxide. Similarly, you can all go balance. You can all go balance the rest of the equations. Let's take a look at the second example, and we'll guide you here. Is going to get slightly a little bit more complicated. And here's the skeleton equation: C3H8. That's propane. It's the gas containing in the propane gas tank. A lot of folks use to cook barbecue, and this is actually the reaction is accounting for the blue flame and the heat extracted from the combustion reaction of propane to actually get the food done, So propane C3H8 react with oxygen gas in the air to produce carbon dioxide. That will be a gas, and the water vapor H2O, that will also be a gas. So let's do an atom inventory first. It's three types of elements: carbon, hydrogen, oxygen, and we have 3 for carbon, 8 for hydrogen, and 2 for oxygen on the reactant side. You have only 1 for carbon, 2 for hydrogen, and 3 for oxygen. So they obviously the equation is not balanced. So which one to choose first? Here comes the trick number 1. If you see any element in the chemical equation, in the chemical reaction, either on the reactant side or on the product side, they are your best friend. Balance those elements last. Balance those last. So in this case, we actually say oxygen should be balanced last. Let's see, we decided actually change a little bit to balance the carbon first. So carbon have 3 on the left side, 1 on the right side. So the only thing we can do is put a 3 as a coefficient in front of carbon dioxide, And we are doing the recount. 3 carbons, 2 hydrogens, because we didn't change the water anyway. And now you get 7 oxygen. This is coming apart. You got to be very careful about counting all the oxygens. There will be 3 times 2, will be 6 from the 3 carbon dioxide molecule. You only have 1 from the 1 water molecule, so you have a total 7. So the carbon is balanced, but the hydrogen is not. Let's take a look at how you get the hydrogen balance. You put 4 here, so you did not change the number of carbons. Now you only change the number of hydrogen and also the oxygen. This is where you want to be extremely cautious when you're counting. 3 times 2 will be 6. Now it's plus 4 times 1. You have total 10. So now in this case, the carbon is matched, the hydrogen is matched. The only missing one is oxygen. How am I going to change the coefficients in front of the oxygen gas, O2, to get it perfectly balanced? And it's a simple math. You put a 5 in front of O2, then you can have all of them matching each other. 3 carbons, 8 hydrogens, and 10 oxygen now. So now we have a balanced chemical equation. Okay, so those are what those smiling faces for. They are balanced. Let's take a look at another example, and here is also a combustion reaction. Now slightly changes. Instead of propane, this is called ethane, C2H6, react with oxygen gas to produce carbon dioxide and water vapor. Same thing, same process again. Atom inventory, three kinds of elements: carbon, hydrogen, oxygen, and 262 on the reactant side. And on the product side, you have 1, 2, 3, and definitely unbalanced chemical equations. And you also notice that oxygen O2 is an element. As we said before, treat that as your friend. Balance the oxygen last. So pick on the carbon. So you put a 2 here, 2 in front of carbon dioxide. You'll have 2, 2, 3. 2, 2, 3. Don't forget to add on the third oxygen from the water side. And now we're looking at, pay attention to the hydrogen now. Put the hydrogen now. So we'll put a 3 here. And immediately it's 2, 6, 7. And now the hydrogen and the carbons are balanced. What's going to happen to the oxygen? Now you're looking at it, the oxygen, you need 7 from the O2, and here comes a little bit dilemma. How could you get 7 oxygen atoms out of O2 oxygen molecules? Each one will give you 2. Here's the solution. Is actually using the fraction 7 over 2. If you have a 7 over 2, literally that's a 3.5 oxygen molecules. Each one gives you 2 oxygen atoms. You can have 7 oxygen atoms. So you put a 7 over 2 here and recount. You have 2, 6, 7. Matched with carbon, matched with hydrogen, matched with oxygen. Voila, everything's fine. Except, how could you have a fraction as the coefficients? That comes in as a dilemma again. So because we talked about it, all those coefficients are integers, whole numbers, and not a fraction, because things you cannot get a half of oxygen molecule. How are we going to resolve that? But remember, now we just established all of the number of atoms for each any given elements are perfectly matched, so it's called a balanced chemical equation. Now essentially this is called, the arrow is acting like an equal sign. If you have a balance, you have an equal sign, kind of equal, left side equals right side is the equation. What can you do? Kind of mathematically, you can actually multiply both ends by the same non-zero number. The equal sign still holds. Then here comes the strategy. You multiply the left side by 2. The reason why by 2 is you want to get rid of the half. So when you multiply 7 over 2 by 2, you're going to get a 7. But on the other hand, you have to do it exactly the same thing on the right side of this chemical equation. So multiply that by 2. So now we start counting again atom inventory. Now you have 4 carbons, 12 hydrogens, and 14 oxygens, because this one is 2 times 7 over 2, you got a 7, and 7 times 2, you got 14. You got exactly the same number on the right side, the reactant side. So this is perfectly balanced 2. So now I start looking at the final form of this balanced chemical equation. And you have 2, 7, 4, 6. Do a final atom inventory count to see whether we have it balanced. You have 4 for carbon, 12 hydrogen, 14 for oxygen. 4, 12, 14. Perfectly matched. We had arrived at a balanced chemical equation. So don't be afraid when you're trying to balance the chemical equation. Use fractions. Use a fraction as coefficients. However, that's not the end of a balanced chemical equation. Since the fractional coefficients are not allowed, then you have to normalize. You have to take the denominator, multiply both ends by it to get rid of it. Here are some exercises and problems, and trying to utilize the process I just laid it out. laid it out there. The number one is the skeleton equation atom inventory, and then you go by the strategy. The number one is if you see any elements, that's your best friend, balance that particular element last. Those are a bunch of exercises. I'm pausing for 10 seconds. You should pause the player and get a piece of paper out and start working on those problems. Not easy. It's going to take time to accomplish that. It's going to take time to accomplish that. Okay, let's continue, and I'm going to show you the next slide will contain the answers for those exercises. Compare with what you got on the paper and to see any mistakes were made. If so, trying to figure out how you made those mistakes. Let's move on. Take a look at example number 4. Skeleton equation is this lengthy one. Aqueous solution of barium chlorate is mixed with sodium sulfate. Produce white precipitate that will be barium sulfate plus sodium chlorate aqueous solutions. If we do it the traditional way, atom inventory, so you have barium, chlorine, sodium, sulfur, and oxygen. You have 1, 2, 2, 1, 10. On the reactant side, you have 1, 1, 1, 7 on the product side. Remember, you have to add all the oxygens together. Try this, and pretty soon you will find a little bit frustrating. It's unbalanced is the word to start. There are a lot of elements, and now it's coming down. Have you noticed something here? You can pause the player, take a look at it, and try to figure out the pattern. You see the sulfate, right? You see the sulfate. Sulfate on this end, the sulfate on the product end, on the reactant and the product ends. And also see chlorate, the CrO3 minus ion, polyatomic ion. They're on this side and they're also on that side. So for those ones you're looking at, those are polyatomic ions involved in the chemical reaction, but they have not changed from the reactant side to the product side. Okay, so this is the one coming down trick number 2. If you observe polyatomic ion that do not change during the chemical reactions, you assign it as a single unit. And now you start changing this equation. When we do the atom inventory now, we slash to it, say it will be slightly different. This will be counted as quote-unquote atom inventory, and now we have treat each polyatomic ion as a single unit. So atom inventory becomes we treat the barium ion as one, the chlorate ion as 1 unit, sodium ion as 1 unit, and the sulfate ion as 1 unit. Now you can see I have 1 barium, 2 chlorate, because this is a CrO3 parenthesis 2, and 2 sodium, and 1 sulfate. On this end, you have 1 barium, 1 chlorate, 1 sodium, and 1 sulfate. So we pick sodium ion to start with, put a 2 there, and you will have immediately 1, 2, 2, 1. And then immediately you can say, wow, they actually perfectly match. So this actually makes the process much, much simpler. Much, much simpler. Let's take a look at example number 5. Example number 5, aluminum hydroxide aqueous solution was mixed with sulfuric acid, H2SO4, aqueous solution. You produce aluminum sulfate, that's aqueous solution plus liquid water, So now it is, you can say it's definitely now balanced. Then you have polyatomic ions, sulfate on both ends. And then you have a hydroxide on this end, but you do not have one on the other side, the reactant side. So here comes the third strategy is when the water is formed in this type of reactions, you treat water as a H-OH. You treat it as a hydrogens linked to the hydroxide group. So you can break it down in here. So that now you'll have the hydroxide group on each end. this is crucially important. Now, when you have this, you have the quote-unquote atom inventory now. You count aluminum ion, hydroxide ion, polyatomic ion, hydrogen, and sulfate ion. You have 1, 3, 2, 1 on the reactant side. You have 2, 1, 1, 3 on the product side. So you pick to balance the aluminum ion first. You put a 2 here. Now you have 2, 6, 2, 1 on this side, and now you start to balance the OH. You put a 6 in front of here. You have 2, 6, 6, 3, and now the hydrogen is now balanced. So now you put a 3 on here. You have 2, 6, 6, 3. Difficult part, actually, they are all balanced. The difficult part about this approach is you have to separate the polyatomic ion out, and wherever you do that, do not count the atoms within the polyatomic ion add to the total number for the individual element. Let me repeat that. When you have this approach, you do not take the polyatomic ion and add the individual element back to the total number for individual element. In this case, when you count H, you do not count the H in the OH. Okay? So those are the exercises. And again, take the piece of paper out, start working on this. Use the processes I outlined in this presentation. It will save you a lot of time, and you can get correct answers all the time. I pause here for 10 seconds, and then you can pause it, work on those problems, then check back with the answers I'm going to present to you. Here are the answers to those exercise questions. Check with your answers to see whether you get them correct. So with that, I close the presentation, and hopefully after this you are going to become an expert in balancing chemical equations. Thank you very much for your attention.